You've definitely heard the term before. Acid rain. It sounds pretty scary, right? Destructive, ominous, but what is it really? Let's get past the name and dig into the subtle science behind this silent erosion.
So, when you hear acid rain, what pops into your head? Is it some flesh-melting, car-dissolving downpour straight out of a disaster movie? It's a pretty crazy image, but the reality, well, it's way less dramatic and honestly a lot more interesting.
The whole truth is really all about chemistry. You see, believe it or not, even normal clean rain is already a little bit acidic. It has a pH of about 5.6. Acid rain is just rain that's become even more acidic. For example, back in the year 2000, the most acidic rain here in the US had a pH of about 4.3. So no, it's definitely not going to melt you on your walk home.
And this slide really puts that into perspective. A pH of around 4.2, that's basically the same acidity as your favorite can of soda. Some acid rain has even been measured at a pH of 2.4, and that's pretty much straight up vinegar. Now just imagine vinegar falling from the sky for decades. You can start to see how that might cause a few problems, right?
Okay, so what's happening chemically to make our rain acidic in the first place? To figure that out, we have to shrink way, way down and take a look at what goes on inside a single little water droplet, floating around in a cloud.
First, just a super quick refresher on pH. It's the scale scientists use to measure acidity, and it runs from 0 to 14. Pure water? That's neutral, right smack in the middle at a 7. Anything lower is acidic, anything higher is alkaline. The only thing you really have to remember is this: the lower the number, the higher the acidity. Simple as that.
And that's exactly why even the cleanest rain is never perfectly pH neutral. Our atmosphere is naturally full of carbon dioxide, or CO2. So as water droplets are forming, they dissolve some of that CO2, and that creates a very weak acid called carbonic acid. It's this simple little reaction that gives all rain a slightly acidic starting point, right around a pH of 5.6.
So if a little bit of acidity is totally normal, what happened to tip the balance? Well, it turns out we started adding a couple of extra, invisible ingredients into the atmosphere, ingredients that make a long journey from our smokestacks all the way up to the storm clouds.
The main culprits here are two groups of pollutants: sulfur dioxide, or SO2, and nitrogen oxides, or NOx. You can think of them as the raw ingredients for acid rain. When they get up into the atmosphere, they react with water and oxygen, and they create acids that are much, much stronger than that natural carbonic acid we just talked about.
So where did these gases even come from? Well, some are from natural sources like volcanoes, but the vast majority is man-made. Just look at this breakdown. About 2/3 of all sulfur dioxide and about 1/4 of all nitrogen oxides come from burning fossil fuels just to make electricity. The rest? That comes from our cars, trucks, and factories.
And here's a really critical piece of the puzzle. This pollution doesn't just stay put. The winds can carry these chemicals for hundreds, even thousands of miles across state and national borders. That means a beautiful, pristine forest can be damaged by acid rain that was caused by a power plant in a city halfway across the continent. It really is everybody's problem.
And this long-range pollution, well, it leads to what can only be described as a silent erosion. The damage isn't instant or dramatic like in the movies. Instead, it's slow, it's cumulative, and it has a massive impact on both our natural world and all the incredible things we've built.
You know, one source we read had a perfect analogy for this. It described the process as acid rain dissolving structures like water does to a sugar cube. It's not a violent explosion. It's just this slow, steady wearing away that is incredibly destructive over a long period of time.
And you can actually see that sugar cube effect happening right here on these stone structures. On the left, you've got a marble baluster with these black crusts on it. That black stuff, it's a mineral called gypsum, and it forms when sulfuric acid in the rain reacts with the marble. It traps dirt, and then it flakes off, revealing crumbly stone underneath. On the right, you can see where rain has just washed over a column for years, slowly dissolving the stone and softening all those sharp, beautiful carved details.
The impact on ecosystems is just as devastating. Acid rain seeps into lakes and streams, lowering their pH so much that fish eggs can't hatch, and even adult fish can't survive. It also strips essential nutrients like calcium out of the soil, which trees need to be healthy. And at the same time, it releases toxic aluminum from the soil into the water, which poisons aquatic life and damages tree roots.
So, acid rain is a mostly invisible chemical process. But there's a related phenomenon that often gets confused with it, and this one is a lot more dramatic and way more toxic. It's time to meet black rain. You can think of it as acid rain's dangerous cousin.
The key difference is right here. Acid rain is all about dissolved chemicals. Black rain, on the other hand, is about physical particles. See, all rain forms around a tiny nucleus, usually a speck of dust or salt. But for black rain, those nuclei are radioactive ash, or thick soot and oil from a massive fire. That's why it's physically black, oily, and sticky. It's literally carrying the disaster down to the ground with it.
And yeah, the causes of black rain are just as extreme as you'd imagine. We're talking about catastrophic, high-energy events. Things like the nuclear detonation over Hiroshima, the massive oil well fires in Kuwait after the Gulf War, or enormous wildfires and volcanic eruptions. These events blast huge volumes of soot, ash, and debris up into the atmosphere, which then gets washed out by the rain.
Okay, these are obviously very serious problems. But here's the good news. We actually have a history of tackling them. So let's look at the solutions we found for acid rain, and also take a quick look at how these pollutants affect our own health.
Believe it or not, the fight against acid rain is a major environmental success story, and the science isn't even new. The link was first made way back in 1852. By the 1970s, it was a huge public issue, and that led to the 1990 Clean Air Act amendments in the US. This created a clever cap-and-trade system to cut emissions, and guess what? It worked. By the 2000s, SO2 emissions had dropped by a whopping 40%.
And that work still continues today. Programs like NAPAP are still running studies to better understand exactly how acid rain affects our lakes, our forests, and our buildings. This research helps us pinpoint the most effective ways to protect both our natural world and our priceless historic structures.
So what about our health? This is really important to know. The danger isn't direct. Walking in acid rain or even swimming in an acidic lake is perfectly safe. The real harm comes from breathing in the ingredients of acid rain, those tiny sulfate and nitrate particles floating in the air. They can get deep into our lungs and have been linked to serious heart and lung problems like asthma and bronchitis.
When you think about it, the fight against acid rain was one of the defining environmental crises of the 20th century. It really taught us that science, public awareness, and strong policy can come together to solve massive, cross-border pollution problems. So the question that leaves us with is this: as we face new and even more complex atmospheric challenges in the 21st century, have we learned those lessons well enough?
Hey, if this explainer helped you understand the science behind the headlines, please do us a favor and hit that like button and subscribe for more deep dives. Thanks for watching.